All right. Good morning. Let's get started. So the first thing I want to do today before we get into any problems is talk a little bit about the exam, which will be either Wednesday or Friday, depending on which group you're in. And as I have written up on the board here, if you're in groups B or C, I believe groups A and B are in here today, correct? So groups A and B are in here today. Typically, Wednesday is groups B and C. So if you typically come on Wednesday, then you are taking your exam on Wednesday. And then those of you in here that are in group A, your exam will be on Friday. Okay. So if it's not your day for exam, you don't have to come. So if you would normally come on Friday, don't come unless you're in group A and that's your exam time. Okay. Then we have a little bit to talk about in terms of like what to expect on the exam. So this is exam number 1, review. And one thing that I will tell you is that typically I don't try to trick you on exams. And just this morning I did post an old exam on Foxtail. So if you want to look at one of my old exams and get a feel for what my exams kind of feel like and one that I've written before, the one that I write obviously won't be the one that's on there. And sometimes I almost hesitate to put practice exams up, and I'll tell you why. Is that people spend a lot of time doing the practice exam when really they should just be working more problems. Okay, the best way to prepare for any exam in calculus is to work more problems that are like the problems you did in the homework. Okay, so just doing the practice exam is not enough studying for this exam. All right, so if that's all that you do to get ready, you're probably not going to be prepared. But that said, I did put one up there, more just for you to get a feel for what an exam difficulty looks like for me, not so much so that you could just use that as your only way of studying. Okay, so as you study for this exam, I would just do a lot of problems. A great way to study for a calculus exam is to get a small group together, go into math lab, just somebody picks a random problem from the book, you write it on the board, and then you try to solve it together. Probably an odd problem so that you can see what the answer is in the back of the book or something like this. Pick some problems and try them. That's a good way to go. And then if you do get stuck and you don't know what's going on, you have the tutors right there to maybe give you some help. So that's just a suggested way to do it. Everybody kind of has their own thing. Okay, so let's talk about what will be on this exam. Of course, one of our major themes of this exam is limits. And that's where we've spent most of our time so far in this class. But what do you need to know about limits? So you need to know how to calculate limits algebraically. And by that I mean, what are all the ways that we've learned to just calculate a limit? You could just plug in the number in some situations. Sometimes you have to multiply by a conjugate. Sometimes you have to factor. So there are different things. I will tell you that something I won't put on the exam is I won't put on some table, okay, where you have to fill out a table and then say what the limit is based on the table. I won't do that because we don't have calculators on the exam. Okay, so all of the limits on the exam will be limits that you can do without a calculator. Okay, so first thing, so we have all these things like factoring, multiplying by conjugate, these algebraic ways of calculating limits. Then we talk about infinite limits. So that's if the limit itself is infinity or minus infinity. And we know when a limit is going to be infinity or minus infinity because there's some factor on the bottom that there's no factor on the top to cancel it out, right? So when we're in that situation where we have like an x minus 2 on the bottom, but there's no x minus 2 on the top to cancel it out, we're like, oh, okay, this is an infinite limit. And then we just have to figure out, is it going to positive or negative infinity? Okay. Then we talked about limits at infinity. And this is when you're actually taking a limit as x goes to infinity. These also go along with horizontal and vertical asymptotes and finding horizontal and vertical asymptotes. So horizontal and vertical asymptotes. I think I spelled that right. Asymptotes. Okay, so you should be able to find horizontal and vertical asymptotes using both infinite limits and limits at infinity. I didn't write this down up here, but you should remember it, and that is you should be able to also talk about the right hand and left hand limits. So right hand and left hand limits. Then we talked about continuity. And so you should be able to tell where is a function continuous or where is a function not continuous using some algebra. And then in that section, we also talked about the intermediate value theorem. I usually abbreviate it, but that's the intermediate value theorem. And you should be able to use the intermediate value theorem to do some things like remember the type of problem where they say, okay, well, on one side of the open interval, this thing is negative. On the other side of the interval, this thing's positive. So somewhere in between, it must be 0, right? So you could solve that kind of a problem for me where I say, show that on the interval 1 to 2, there has to be a place where this equation is 0. You remember those types of problems. So that's the type of problem I would probably ask about the intermediate value theorem. Okay. Then we got into derivatives. And we haven't done a lot yet, but we've gotten some things. First of all, we've using a limit to find the derivative at a point. We also call this the definition of a derivative. Okay. So the formula that I would be referring to here is like that f prime of a is the limit as h goes to 0 of f of a plus h minus f of a over h. So using that formula to find a derivative at a point. And if we can find the derivative at a point, then typically we can also find the equation of a tangent line. So we should be able to do that. So find the equation of a tangent line. At a point. And then finally, we should be able to find what we call the derivative, which is f prime of x, which is what today's homework was about, right? Just finding the actual derivative function using the definition of the derivative. So this one's just using that f prime of x is the limit as h goes to 0 of f of x plus h minus f of x over h. And that is about it. Any questions for me about anything that you see on here or anything maybe that you don't see on here that you're wondering, could that be on there? Okay, so yeah, that's it. And like I said, I'll say it one more time. I don't really try to trick you. Okay, so if it's a kind of thing that you've seen on your homework, then that's the sort of thing I typically put on the exam. So going back over old homework assignments is a very good way to study for the exam. And doing problems that are kind of like the problems that were on the homework, that's a good way to study. So just do a bunch of problems, make sure that you know how to do each of the major things that we've done, and you should be fine. So, questions? Yeah.
Can we get answers to the homework?
Can you get like,
Are they posted at all?
they are not right now. I can get you the like odd numbered ones.
Yeah.
Yeah, I don't know if I can get you the evens easily. But I might be able to get you the odds. So I'll try to get that posted today. Okay. Okay, so moving on from this, any questions about today's assignment? Yes, sir. 16? Okay. Okay, so we've got matching derivatives with functions. We've got some different derivatives here. And we want to know which functions they represent. Okay. Okay, so here's my axes. And then we have like one of these lines, line A, is at about 1.5, right? There's a line right here. This is my x-axis, y-axis, and then I have a derivative line right here. Now, if the derivative is always got the value, so this is like f prime of x. And this says that the slope of my original function is always 1.5. So the slope is always 1.5. And then you go down to the options and you've got a bunch of lines, right? And all of those lines have different slopes. And so, but a slope of 1.5 So I don't know exactly where to start this thing, but I do know that a slope of 1.5, like if you were starting at the origin, you'd go up 1.5 and over 1. Something like this. And then it would be something kind of at that angle, right? Because that has slope 1.5 everywhere. And so then I come back over here and I say, do any of them kind of look like that? And there's only one, right? A. Line A kind of has this slope. And so this one's line A. So this guy maps to A. Does that make sense? And then let's do one more just to kind of make sure we understand. So let's take like, I guess let's just take the next one, B. It's at like 0.5. So let's say that this is g of x. So again, I don't know exactly where the function is, but I do know its slope everywhere. And the slope is 0.5 or 1/2. So for one, if I go 1 up, I go 2 over. So I could put like, and so it has something at that angle, right? So it's going, the slope of this thing is 1/2. And so I could go over here and say, do any of these kind of look like they have the slope of 1/2? And it looks like it's C, right? Because it goes up 1 over 2 kind of thing. So yeah, C. Does that make sense? And then for the negative ones, like the slope is always negative. So it's like going down somehow. And so just looking at this, like negative 1/2, that looks like it's B. And then if the slope is always 2, negative 2, I'm sorry, that looks like it's D. So you're just kind of reading the slope and trying to figure out what the original function looks like. Yeah.
Can you do 21?
21. Sure. Okay, so it says use limits to find the derivative and then evaluate at the given values of A. Okay. So 21. We have that f of x is equal to 5x plus 2. And we want to use the definition of the derivative to find f prime of x and then evaluate it at some points. So f prime of x is the limit as h goes to 0 of f of x plus h minus f of x divided by h. So let's plug in what is f of x plus h and f of x. This is the limit as h goes to 0 of f of x plus h, which would be 5 times x plus h plus 2. That's f of x plus h. Agreed? And then we say subtract f of x. So I just plug in 5x plus 2. And I need to remember to subtract all of that divided by h. So this is the limit as h goes to 0 of 5x plus 5h, okay, 5x plus 5h plus 2 minus 5x minus 2. So some things cancel. The 5x's cancel. The 2 and the minus 2 cancels. I still am over h. So I get the limit as h goes to 0 of 5h divided by h. And now the h's cancel, which is great. And I'm just left with 5. So what I just did here is I just said that the derivative f prime of x is always 5, no matter what x is. Now, does this make sense? Because what I was trying to figure out here is what's the slope of this curve? But what is this curve? It's just a line, right? And the slope of a line, if this is mx plus b, the slope is always 5. And what we just figured out is that the slope of this line is always 5. It's like, yeah, that makes sense. Yeah.
So what is the one where we have to plug in A?
Yeah, so they take it kind of one step at a time, and soon we won't. So let me explain. So in the last section, what they did is said, what's the slope at a equals 3? And so instead of like just leaving x in the whole time, you start with that a, like let's say a is 3, so you'd have f of 3 plus h minus f of 3 over h, instead of just leaving in the x and kind of solving it for all the x's at the same time, you're solving it for a particular x value, like 3. So it's actually not very productive to do that, although it works for a particular value. So in this case, now that we know how to calculate the derivative, it's kind of like, why would we ever do it for just one value when we could do it for all the values at once and then just get some function that gives us all the derivatives? Does that make sense? But they always usually, when textbooks lay out calculus, they always teach it first in terms of how do I find the slope at just one point? Because honestly, that's what you're doing. But here you're just doing it for all the points at once. So the derivative is defined point by point, but then you can kind of say, okay, so now we could create this derivative function that's all the points. So once we find this derivative function, we really never go back to the a. We'll always just use the derivative function and then plug in the a. And that's what they ask you to do in the other half of this problem, right? Is they say, and now what is it if a is 1 or if a is 2? Well, in this case, f prime of 1, if I plug in 1 to this function, I get 5. And f prime of 2, if I plug in 2 to this function, I get 5. So it's not very interesting at all. It's 5 everywhere. But somewhere else, if there was an x in there somewhere, it would matter. Yeah.
You got it.
Okay.
Thanks.
Yeah.
So the derivative function would just be f prime x at this point.
Yes. So in this case, it's very, very simple. But in some of the other ones, it could be more interesting. Yeah.
So when you do the limit like this regularly and you have like x's in your answer, is that your slope or is that your function?
That's the function that gives you all the slopes.
Okay, so then you plug in a point.
Yeah, so let me give you an example really quick just to hopefully clear it up a little bit. Let's say that your function was x squared. I could do a bunch of work, and then I would get that the derivative function is 2x. Okay, so I could do the work like this and show that I finally get at the end, f prime of x is 2x. Now, what does that mean though? That f prime of x is 2x. Well, the original function, f of x, is a parabola, right? It just does this sort of thing. Correct? And what this says is if you want to know what the slope is at a point x on this curve, so if you want to know that thing's slope, just plug in x to this function and it will give you slope. So this one, if I plug in x, it gives me the position. This one, if I plug in x, it gives me the slope. And let's see if we believe it. So if I plugged in a 0 here, and I said, what's f prime of 0? It would be 2 times 0, which is 0. So the slope at 0 better be 0. And it is. You see what I mean? It's a flat slope at that point. If I said, well, what's f prime at 1? Well, that means I plug in 1 to 2x and I get 2 times 1, or they say that the slope should be 2 when we're at 1. So if I went out to 1, that'd be about right here, and they're saying that this slope is 2. And even though it's a little bit hard to see it, I think it's believable, don't you? That like this does look like it goes over about 1 and up about 2. So yeah, that makes sense. And then if I said something like, well, what's the slope at -1? Then it would be 2 times -1, which is -2. So over here, the slope they're saying is -2. And that's true. Do you see what I'm saying? So this thing that we call the derivative, all it really is, it's all the slopes in one function, which is actually kind of miraculous in some sense that there is such a function that gives us all the slopes at one time. So when we calculate a derivative, we're really just calculating the function that gives you all the slopes, where you start with the function that gives you all the positions, right? So you take the function that gives you all the positions, you take its derivative, and then you have the function that gives you all the slopes. Yeah. Does that make more sense?
Yeah.
Okay, awesome. Other questions? Yes, sir. 17? Okay. 17. Okay, reproduce the graph of f, okay, and then sketch a graph of f prime on the same axis. Okay, sounds good. So 17. First, we'll redraw this thing. We've got a point here. Then we're going off like this. Then we go 1, 2. We go up like this. We go 1, 2 again. We go down like this. Then we go over 1, 2, 3, up 1. Go like this. Okay, so this is my original function in blue. So it says redraw that graph, which I just did. And now with this, on the same set of axes, let's draw its derivative. So here's my question. The derivative is just the slope, right? So my question is, let's forget all that stuff right now and just look right here. This line that we've got, that's this piece of the curve, what's the slope? -1, that's right. So that means that the derivative is -1 here. I'm going to use red for my derivative until it gets to this point. So here's -1. So until it gets here, it's just -1. So it's saying that all along here, the slope is -1. Does that make sense? Okay, so then what happens here, it's kind of a mess because it's different from the right and from the left. So there's no real slope at this point. But then what about in between -2 and 0? What is the slope? 1. So what happens is then it just magically jumps up here to 1 and stays at 1 until it gets here. Sound good? Okay, and then what happens from here to here? What's the slope? -1 again. So it does the same thing. It bounces back down, and it's -1 until we get here. And now they kind of try to trick you a little bit, and they say, okay, what about this last little stretch? What is the slope? 1/3. That's right. So you go up 1 over 3. So rise over run, it's 1/3. 1/3 would be about right here. So it's 1/3 all through there. So the derivative doesn't look very nice, I will say. But this is basically what the derivative function would look like. Yeah.
So at the very last point on the right for the 1/3,
Yes.
you can't make that a point on that, or if you make that a point, or is it when the two lines around the pointer, the slopes are different that you can't determine?
Yeah, so the reason I made this one open and not filled in is because this point right here doesn't have a limit from the right and the left. It just has one from the left. And so I would leave that open. This doesn't come up like a ton or something, but that's the reason I left it open. And ultimately over here, I think this should have been open too. This kind of stops somewhere. And this should have been like this. Yeah.
And then the slope isn't 0 at the point where it changes.
No.
Unlike a curve.
That's right, it's not. Because, okay, if you think of the difference quotient, it's the limit of something, right? It's the limit of a slope. So if it's the limit of a slope, what is the limit right here from the left? Not 0. Oh, I see what you're saying. The limit of the function is 0. What's the limit of the slope? As I get closer and closer, the slope is always -1. So the limit of the difference quotient is -1. On this side, what's the limit of the difference quotient? +1. So at this point, on one side is going to -1, one side's going to +1. So at this point, there is no limit of the difference quotient because they're going to different things. Does that make sense? So that's why I don't put in a point here, is because there's no limit at, I guess it's -2. There is one from the left and there is one from the right, but they're different. So this doesn't have a derivative at -2. Yeah. Other questions? Yeah.
35.
35.
This is just part B.
Oh, yeah. Sure. So what did you get as your answer for part A?
6x plus 2.
Good. Okay, so 6x plus 2. And then you said, what's the equation of the tangent line? So the original function, is it 35, did you say?
Yeah.
35, we have f of x is equal to 3x squared plus 2x something minus 10. And a is 1. Is that right? And so we want to find the equation of the tangent line at a is equal to 1. And so you did some work. And you got the f prime of x for a was 6x plus 2, which is correct. Okay. And so the question is, what's the equation of the tangent line? Well, what we need to find the equation of a tangent line is we need a point and we need the slope. So we need to know what's the functional value when a is 1 and what is the slope value when a is 1. Well, the original function gives me the functional value. The derivative function gives me the slope value. So if I want to know, I want to know what's f of a, but I also want to know what's f prime at a. And in this case, a is 1. So I want to know what is f of 1. Well, f of 1, this is my equation. So it's 3 times 1 squared plus 2 times 1 minus 10. And f prime of a is, so that's 6. well, that's f prime of 1, or just 6 times 1 plus 2, which is 6 plus 2, or 8. This one is 3 plus 2 is 5, minus 10 is minus 5. Okay, so we got a point out of this one. The point that I now know is 1 minus 5, and I know my slope, and that's what I got from my derivative, and my slope is 8. So now I just need to use my point slope equation. So it's y minus y1, which is minus 5, equals m, 8, times x minus x1, which is 1. And now we could solve for y. We get y plus 5 is equal to 8x minus 8. And then just subtract 5 from both sides and get 8x minus 13. And that's it. Make sense? Yeah. So in all of these, if I asked you something like this on the exam, same kind of thing. Find your derivative, but then if I give you like a point A, plug it into the original function to find your point, plug it into the derivative function to find your slope, and then just use point slope equation to find the line. Oh, I've got some people writing on mine. Let me see. Oh. So yeah, somebody asked a question about, hey, I took some calculus before. If I use the calculus that I know to take the derivative instead of using the definition of the derivative or the limit of the difference quotient, will I get marked down on the exam? The answer is yes. You would get marked down on the exam, but here's the good news. You can certainly use anything that you know to check your work. So like if in this problem, I would assume that you use the definition of the derivative to get 6x plus 2. But if you knew that using some other magic that we haven't learned yet, that really I know how to take this derivative an easier way and I would get 6x plus 2, well, at least now you know what the answer is, right? You know what you're trying to get at the end, and that's good in and of itself. So you can certainly use any knowledge you have of high school calculus to help you check your work, but you still have to show it, okay? Other questions? Okay, let me look at what people are saying here. Okay, 35, somebody said, which we did. 19. Oh, okay, we haven't done 19. Oh, yeah, okay. Let's look at 19. Then that will probably be the last one. So 19 asks to use the graph that's given to figure out the values where f is not continuous and the values where it's not differentiable. Okay. So we have -1 and -2. We have 1, 2. Then we go like this. And this one kind of swoops down like this. We have a hole there that jumps up here. Okay. So first of all, let's talk about continuity. And continuity, one way of thinking about continuity is, do I have to pick up my pen to draw it? Right? So is there a hole, or is there a jump? Things that make me kind of have to stop, pick up my pen, and do something. So while drawing this, I go, oh, I have to pick up my pen. So here I would say, this thing's not continuous at 1 because there is a jump at 1, right? So there's a jump discontinuity. So just at x equals 1 is this thing not continuous. So if I were saying where is it continuous, then I suppose it's continuous from -2. Is that what they ask? Is where is it continuous? Guess I should look. Yeah. Oh, not continuous. Okay. Well, that's much easier. So it's not continuous. As x is 1. And then f is not differentiable as. Okay, so the question is, where is it not differentiable? So where can I not find the slope? Well, the first one I see is right here, because coming into this thing this way, the slope is one thing. Coming in from this side, the slope is something else. So the slopes don't match up. Another way of thinking about that is there's a sharp corner. Sharp corners are bad for differentiability. Okay, so at 0, at x equals 0, it's no good. And I guess the only other question is, what about at 1? Well, let's see. We know that differentiability implies continuity, but continuity doesn't necessarily imply differentiability. What do we think about at the point 1? Is it differentiable? What do people think?
It's not differentiable.
Yeah, and why?
You can't find the slope of the point.
Yeah, so the slope of the point you're actually looking for is this one, not this one. If you were looking for this one, it would work out okay because the slope actually is leading into that point on both sides. But this point is just like hanging out there by itself. There's no limit at that point. So since the point doesn't match up, we're trying to find what's the slope at this point, and that almost just doesn't make any sense, right? So, or at x is equal to 1. Makes sense. So that's that one. Okay, I think that that's a good place to stop for today. Any last minute questions about the exam before we get going? Oh, yeah.
So you can't have a calculator?
That's correct. No calculator. Yeah. Oh, somebody asked, can we bring in any type of notes for the exam? Was that your question? Yeah, good question. No, you cannot bring any notes in for the exam. Yeah.
Is this lockdown or also paper?
Paper. Yeah. Yes, sir.
Will you have any formulas on the exam?
No. No, here's my reasoning for that. And you definitely could take calculus somewhere someday where they would let you have such things as a calculator. And oftentimes, like, you really don't need a calculator for a lot of these problems. It's just factoring, multiplying by conjugates, doing some algebra. You don't really need a calculator, but then like I let somebody use a calculator and I just see them like pounding on that calculator, like they're just gonna like magically, the calculator's gonna tell them something. And it's like, that's not actually that helpful. And I write my tests in such a way where you just don't need it. Okay, there's no there aren't gonna be any decimals, nothing that you need a calculator for. And then on the side of the notes, that also is like a pet peeve of mine. And that is that, like, let's say I let everybody bring in a 3x5 note card. Well, man, I've seen some 3x5 note cards that should go like in an art gallery because people have like really made like the best note card ever. Like every piece of information we studied, they somehow crammed on that note card. And then they get on the exam and they don't do very well because they didn't do problems. And it's like no note card is a substitute for working a lot of problems. And so what I want you to do is actually know the stuff. There's nothing here that you can't remember at this point. If there ever comes a time where it's kind of like, no, this is too much for you to remember, then I would provide a note card. But that really has not happened at this point. And everything that we've done so far, you really do need to know. Like, it's not something that you should just be like, I know it exists somewhere. Like, I know that the limit of the difference quotient is a formula that exists. I don't know what it is. Do you know what I mean? It's like, that's not good. Like, if you're a calculus student, you really should know what is the limit of the difference quotient, like limit h goes to 0, f of x plus h minus f of x over h. Like, you need to know that because we're going to use it so many times in the future that if you don't know it, it's kind of like you're hobbled, so to speak. So what I try to do when I teach this class is I make you learn the stuff that you really will want to know later. And I think that this is actually a place where a lot of math teachers don't do a good job. It's like they actually are like, I can be nice and I cannot make you learn this stuff, but you will need to learn it eventually. But then you're just going to feel like you're behind when you get here. And I'm like, no, you need to know this stuff. And so I'm actually doing you a favor. If you want to look at it that way. I do. Anyway, so that's it for today. Have a great day, and I will see groups B and C on Wednesday for the exam, and then group A on Friday. See you then. Yeah. Say that again.